Alright, we're just going to be going over some quick forces and energy stuff today, review for anyone who needs it. So we've got 3 questions here we're going to go over. Our first one says, a squirrel is being pulled up an incline with an applied force through a distance of 4.7 meters and a height of 1.7 meters. The squirrel starts from rest, and we're supposed to find the final velocity of the squirrel after going 4.7 meters up that incline. So the neat thing about this sort of thing, when nothing is changing, we can use forces or energy. But when something is changing, like our third problem here, we'll get to that, we must use energy. But because this is an AP Physics 1 curriculum, we're going to be using energy because that is going to be the more efficient way to solve this and give us a more direct answer in velocity instead of acceleration and then conversion to velocity through forces. So for this one, our net equation is going to be work is equal to gravitational potential energy because it is an incline, we're being pulled up, plus thermal energy. And we know that there's thermal energy because we're given this mu over here, the 0.33, thermal energy plus kinetic energy. We know that that's a thing because we're giving a velocity. We know this velocity as it starts from rest, so we're looking for the velocity here. So work is going to be equal to force times distance. Gravitational potential energy is mgh. Thermal energy is force normal mu distance plus 1/2 mv squared. Or v squared is what we're looking for. We're looking for the velocity final. Force is of course 61. Distance is 4.7 meters through it, equals m. M is 4.5. G is of course 9.8. And height is 1.7 meters. Now force normal here, what's that going to mean? Force normal is equal to force gravity y. Because this is an incline, force gravity y is going to be equal to mg cosine theta. So 4.5, 9.8. cosine of 21, and then that's force gravity, but we need force friction, so we're going to need to do 0.33, and then the energy of the energy of friction, thermal energy, we need a distance, which is 4.7 meters, and then of course 1/2 m 4.5 v squared, and this is what we're looking for. I might put this in my calculator. 61 times 4.7 is equal to 4.5 times 9.8 times 1.7 plus 4.5 times 9.8 times the cosine of 21 times 0.33 times 4.7 plus 1/2 m 4.5 v squared. Going to get about 8.11 meters per second here. So velocity final is going to approximately equal 8.11 meters per second. And that is that question answered. Alright, time for question 2. So for question 2, figure 2 is going to read, a dog starts from rest and is pulled along a horizontal surface with an angle pull for 7.2 meters. And we're asked to find the velocity, the final velocity of the dog after going 7.2 meters. So just like the last one, we're asked to find a velocity, so we can use energy because nothing here is changing. Energy is going to be faster. The difference is this time it's an angle pull instead of pull up the incline, where the angle is the same as the object being pulled as the force. Here, the force applied is going to be at an angle, and the object is implied to be staying on the ground. That changes the math just a little bit, but it's simple nonetheless, and we're going to go ahead and tackle that. And because it is an angle pull, our equation is going to look a little bit different. It's just going to equal work, and of course we have our kinetic energy plus thermal energy. There's no gravitational potential energy because we're staying flat along the ground. So we're going to do what's called a dot product expansion. So force dot distance, and really that's just the more professional way of writing. Force distance cosine theta is equal to kinetic energy, which is of course 1/2 mv squared plus thermal energy, force normal mu, and then distance. So this is where it changes a little bit. For force normal, because this is an angle pull, force normal is going to be equal to force of gravity plus or minus the force applied in the y direction. So in this case, force normal is going to equal mg, of course, for gravity, 12 times 9.8 minus the force applied in the y direction. So here, that's just going to be 52 sine of 28. Make sure we're in degrees here. when we solve this, we're going to get about 93.2 newtons. So force normal is equal to just about 93.2 newtons. And we can solve that, we can put that into our equation over here. So force, of course, start over here this time. 52, the distance is 7.2 meters, times the cosine of 28. That's not the right spot. Cosine of 28 degrees equals 1/2 m12 velocity final square. That's what we're looking for, plus 93.2, because that's what we just solved for force normal being equal to. Mu is 0.19, and then distance is going to be 7.2. When I solve this in my calculator, 52 times 7.2 times the cosine of 28, cosine of 28 is going to be equal to 1/2 12 velocity squared, plus 93.2, because that's our force normal, times 0.19 times 7.2. And our velocity final for the dog is then approximately going to be 5.82. That's not a good, let's do this over again. 5.82 meters per second, and that is question 2 answered. Alright, for question 3, our caption for the picture reads, a toy car is launched with a spring on a horizontal surface, and then it goes up an incline and comes to a complete stop. Ignore any friction forces, and we're supposed to determine how far up the incline the toy car goes before coming to a complete stop. So this is an interesting one in reference to these other two. In these other two questions, there's no sort of, everything is constant, meaning all the forces applied are constant, there's nothing changing. In question 3 here, we have a spring, and spring means things are changing. So what does that mean? We are forced to not use forces, and we must use energy to solve this one. And this is an example of a problem where we can use the law of conservation of energy, which just means everything from the start has to equal everything from the end. Sum of all forces and energy must be 0 in a system like this. So that means our equation in this instance is going to be spring energy, elastic potential energy is going to equal gravitational potential energy. So let's unpack this for a second. First thing we should notice from the question is that there's a spring, which obviously we have. So we have to use energy, and we got this in our elastic potential energy here. Second thing is no friction forces. No friction, so there's no thermal energy term here. The third thing is that there's no kinetic energy. And why is that? That's because it says multiple times, it says the car comes to a complete stop up here, it says it down here, and importantly it's in the part we're looking for, so we don't have to add it down here. So there's no kinetic energy, just spring to height energy, gravitational potential. So our elastic potential energy is going to be equal to 1/2 kx squared. Make sure to keep that squared when you solve it. It's equal to mgh, where k in this equation here is equal to the spring constant, and x is the compression distance. We're given those, so we don't have to worry about solving for those. So 1/2 kx squared, 1/2, or 50 times 0.65 squared, keep that in there. Mass is 13.5, that's just the mass of the car. G, universal gravitational constant, 9.8, and the height. So we're going to solve for the height, but this is a two-part question, so we're not quite done yet. And so, when I solve for this in my calculator, I'm going to get 1/2 times 450 times 0.65 squared, 13.5 times 9.8 times the height. The height is going to be approximately equal to 0.719 meters. But this is not the answer to the question, because the car is starting on a flat surface that we're considering the y origin, that's 0. So that just means that this is 0.719. And the car is up here because its launch comes to a complete stop at this point in time. On this side of the equal sign, it's at a complete stop because that's what we're looking for. So it's up here. We're looking for this distance. What is this? We'll call that x. And what can we do here? What is this? This is a triangle, right? And we have our favorite middle school acronym here, SOHCAHTOA. And what can we use here? We have an angle, of course. We have hypotenuse that we're looking for, and we have an opposite side from that angle. So from this, we can use sine. So we can set up a little trig equation here. So the sine of 32, again make sure you're in degrees, is equal to the opposite 0.719 over x. And then when we solve this, sine of 32 is going to be equal to 0.719 divided by the distance. We're going to get x is equal to approximately 1.36 meters, and that is our answer. So what we did here is we found the distance here, we found this height here, and we applied trig here. So x is no longer going to be that, x is 1.36 meters, and that is how far the car went up the incline. Alright, on to question 4. The second half of the questions here. Figure 4 reads, a bowling ball starts at 37-degree angle and is given a starting velocity of 2 meters per second. It then goes down and hits the bowling pin, and we're supposed to determine the velocity of the bowling ball just before it hits that pin, just in that infinitely small instance before it touches that bowling pin. So this is a pendulum here, and pendulums are a little bit unique because there are some things you need to know about them in order to calculate this. So if we call this distance L, of course, that's just the distance of the string holding the ball. L is also right here along this thing here. And this H is going to be equal to L minus L cosine theta, and theta is of course that angle. So that's just a unique thing about pendulums. I put that in there because that's something that isn't given. It's some prior knowledge you might need to have to solve this one. So I just stuck it in there for convenience's sake. So the first thing we need to find is height. So H is going to be equal to L minus L cosine theta. And because we have 3 here as our length, our height is going to be equal to 3.0 minus 3.0, no, not that, 3.0 times the cosine of 37. And when we put this in our calculator, we see that 3 minus 3 times the cosine of 37. Height is going to be equal to approximately 2.604 meters. And of course, we're just using obligatory obscure names here. It doesn't have to be height. It could be literally anything, but H is just convenient, and that means height. So with this information, we can create our equation. So we're going to be using the law of conservation of energy here again. So our equation is going to be equal to gravitational potential energy plus kinetic energy equals just kinetic energy. Now let's unpack this for a second. What do we know about this? So we're given a starting velocity, and that's unique because kinetic energy is going to be on the left side. The first instance, before anything starts, kinetic energy has to be here because we're given this 2 meters a second starting velocity. We have to factor that in here. And the last part, we're given just kinetic energy because we're asking just before the velocity, just before it hits the pin. And so for all intents and purposes, there's not going to be gravitational potential energy, just kinetic energy because it's still moving, and that's what we're asking to find. So gravitational potential energy is just mgh plus 1/2 mv squared equals 1/2 mv squared. So at first glance, this might look like, well, I can't solve this. I don't have a mass for the bowling ball. That's okay. With our math magic, we can go ahead and cross out all these mass. All m doesn't need to be there because we don't have an m term, and it happens to cancel out on both sides of our equation. So in reality, our equation is just gh plus 1/2 v squared equals 1/2 v squared. And we'll call this v final squared, v initial squared. So gh, g is of course 9.8. Height we did solve for, so we're going to draw an arrow here, is 0.604 plus 1/2 2 meters a second squared, because that's what we're given as our starting velocity over here. We have to factor that in here. And that's going to be equal to 1/2 velocity final squared. And the velocity final is what we're looking for because that's right before it hits the pin. So if I put this in my calculator, 9.8 times 0.604 plus 1/2, make sure to square the velocity 2 squared, equal to 1/2 velocity final squared. Velocity final is approximately going to be equal to 3.98 meters per second, and that is our answer to the pendulum problem over here. Alright, question 5. This one reads, a bucket is on a rope and is being pulled upwards with a constant acceleration through a height of 12 meters. Assume that the bucket starts from rest. And we are tasked with determining the average power of the bucket through the 12 meters. So this one is a multi-step question, but it's nothing we can't handle. So we're going to go ahead and use forces to solve this because that's what we need to get this part of it done. So we're given a pretty good picture up here. We don't have to draw a free body diagram if we don't want to. Of course, it looks something like this. Not with those kin lines there, just something like that. We don't need that because we're given a pretty good picture. So from this, we can say that our force net is going to be equal to force applied minus force gravity. And per Isaac Newton, force is equal to ma, so force net is equal to ma. Always plug that in there. Force applied, we don't quite know. We'll keep that as force applied minus force gravity, which is of course just mg. So ma, m we give is given as 6 kilograms. A is of course 3.4 meters per second squared equals force applied minus m6 g 9.8. So when we solve this, it's going to be 6 times 3.4 equal to x minus 6 times 9.8. And our force applied is then going to be equal to 79.2 newtons. Exactly. And this question we're looking for average power. So average power is going to be equal to force, distance, over time. So this is really what we're looking for. So now that we have our force applied here, we know the distance is 12 meters, so that's covered. The only thing we're missing here is time. So that's what this equation is for, multi-step question. So S is equal to velocity initial multiplied by time plus 1/2 acceleration by time squared. So we can just solve for time here. So S, we know that's 12, the distance is being pulled. Velocity initial, it says it starts from rest, so there's no velocity initially. T squared, not T squared, just T, plus 1/2 acceleration, 3.4 meters per second squared, T squared. When we put this in our calculator, 12 is equal to 0 t plus 1/2 3.4 x squared. Time is going to be approximately equal to 2.66 seconds. Now we can go ahead and find average power with these two things in mind. And with the distance is equal to 12 meters, we can use the average power formula. Power average is equal to force distance over time. And so average power is of course going to be equal to 79.2, distance 12 meters, over time 2.66. And we put this in our calculator. We see 79.2 times 12 over 2.66. Excuse me, 79.2 times 12 over 2.66. Average power is then going to be equal to, that's not a good P, they're going to be equal to just about 357 watts, because that's what power is measured in, is watts. And that is the answer to question 5. Alright, question 6, just this question over here, pretty easy one to end on. And it says, a pack of cola is sliding to a complete stop along a horizontal surface in 6.2 meters. And we are going to determine the coefficient of friction between the cans and the surface. So this is a pretty easy one. This picture just tells us that we have a velocity of 3.3 meters. So our law of conservation of energy, we're going to be using that. Our equation is just going to be kinetic energy is going to turn into thermal energy by the all ending. And this is just saying that as it moves, energy is turned into thermal energy, which is not conserved, so the thing is going to stop. And it does confirm that, so it's coming to a complete stop. And so let's turn this into numbers here. Kinetic energy is 1/2 mass velocity squared equals thermal energy, which is force normal, mu, distance, and we're going to go ahead and write this out again because there's no incline or anything, so it's 1/2 mv squared equals force normal. Here is just force of gravity, same thing, mu, and then distance. So again, just like the pendulum one over here, maybe we can't solve this, it looks like at first, but we can. In reality, we just cross out our m's. So in reality, our equation is 1/2 v squared equals g mu distance. So we can solve this, get everything. We need to find that coefficient of friction. 1/2 velocity is 3.3 meters a second, because that's what we're given up here. So velocity equals g is of course 9.8. Distance, it says 6.2 in the question, and then we can find mu there. And because multiplication is commutative, we can move that stuff around. So it's going to be 1/2, 3.3. Oh, don't forget to square that. Almost forgot to square that. Make sure you square that. 9.8 times 6.2x. And our coefficient of friction is just going to be equal to about 0.90. And our coefficient of friction is in fact a unitless measurement, so we just put 0.090, and that is the answer to question number 6. Really easy one there.